Chemistry with Nathan Fox. Today we're going to be covering how to draw Lewis dot diagrams. You should already know what these terms are. Valence electrons, single, double, and triple bonds, orbitals, and the electronegativity trend on the periodic table. Okay, so Lewis dot diagrams are a way of drawing molecules so that you can see how the atoms are bonded together where all the electrons are placed in those bonds. Now, in bonding, only the valence electrons matter. So the number of those comes from the group the element's in. Group 1 elements have one valence electron, so hydrogen, lithium, sodium, potassium. All these elements have one valence electron. Group 2 have two valence electrons, like calcium or magnesium. Transition metals, everything in these groups right here, they vary. You don't really need to worry about them. It depends on their charge. Now, if you start from this other end, noble gases have 8 valence electrons. They don't bond. They're done. They're happy. They don't need any more electrons, or they don't need to lose any more electrons. Group 17 right here, these elements have 7 valence electrons. Group 16 has 6. You subtract 10 from the group number for the nonmetals. Group 17 has 7 valence electrons, 16 has 6, 15 has 5, 14 has 4, so on. Okay, so let's look at this example. We are going to draw, let's do a water molecule. Okay, H2O. That's water. So you're going to start with the number of valence electrons you have available, and you have to use all of them. So let's go back to our periodic table. How many valence electrons does hydrogen have? 1. Very good. Okay, so then there's 2 of them, so that's 2 electrons. And then you have 1 oxygen, which subtract 10 from the group number. How many electrons do you have? 6. Very good. Okay, so you have 6 plus 1 is 8 valence electrons. So 6 plus 1 equals in total 8 valence electrons. That's how many you have to use. Now, when you're placing them, you're going to start with arranging all of these atoms, and you represent them with their chemical symbols, like H and O. So you're going to have 1 O and 2 H's. Each molecule is going to have a couple of center atoms. These will be the least electronegative atoms. Now, if you remember, electronegativity goes from francium, which is the least electronegative, to fluorine, which is the most electronegative element. So, now there are a few exceptions to this. Hydrogen never ever goes in the middle, and you'll see why in a second. So you never put hydrogen in the middle. In that case, this leaves only oxygen. So you start with oxygen, then you're going to arrange the rest of the atoms around it. So hydrogen and hydrogen. You're going to link these with single bonds represented by lines. So there's our original skeleton. Oxygen, 2 hydrogens, linked with single bonds represented by lines. So each bond represents a pair of electrons. This is 2 electrons. This is 2 electrons, which means we've used 4 electrons, which means we have 4 left to use. Now, the octet rule. Now, there's something called the octet rule, which means that every atom wants to end up with 8 valence electrons in their outer shell. That's it, 8. Now, noble gases, they already have 8. So they don't react with anything. They've got exactly what they want in their valence shell. 18 minus 10 is 8. They've got all they need. Now, there are some exceptions. Hydrogen only wants 2 electrons, because that's all it has room for. 1 s orbital, that's it, 2 electrons. Boron, beryllium, right here, boron, beryllium, satisfied with 6 to 8 valence electrons. They don't have to have 8, but they can. And then any element in the 3rd period or lower is happy with at least 8. Which means sulfur, phosphorus, palladium, tellurium, strontium, barium, they can all exceed 8. Iodine, they have to have 8 because they have to fulfill the octet rule, but they can all exceed 8. Boron, carbon, oxygen, beryllium, they can't exceed 8. So if we go back to here, everything has to fill the octet rule. You recall, hydrogens only want 2 electrons, so each of these lines is 2 electrons, each of these single bonds. So this one's satisfied because it's got 2 electrons, it's sharing with oxygen. And this one's satisfied because it's got 2 electrons, it's sharing with oxygen. Oxygen, however, follows the octet rule, and it wants 8 valence electrons. Right now, how many does it have? It has 2 over here, and it has 2 over here, which brings the total to 4 valence electrons. It needs 4 more. What a coincidence. We have 4 electrons left. That makes it perfect. There are these things called lone pairs. You can't add any more bonds because that will exceed the octet rule for hydrogens. It doesn't want any more electrons. You can't make this a double bond, you can't make this a double bond. You can't add them to the outside of the hydrogens as lone pairs. That leaves one place, the oxygens. You're going to put a lone pair there, that's 2 electrons. You're going to put a lone pair here, that's 2 electrons. And then that leaves the oxygen with 1, 2, 3, 4, 5, 6, 7, 8 electrons. Everyone's happy. -4, 0 valence electrons. Perfect, you're done. That's it. Let's do another. Okay, so let's do another one. Let's do CO2, carbon dioxide. Now, let's count the valence electrons. Carbon has 4 valence electrons, 14 minus 10. And then the oxygens we established had how many electrons? 6, that's right. So 12 plus 4 is 16. So we have 16 valence electrons to use. Start with the least electronegative, remember that. That would be carbon, because if you remember, it goes from francium to fluorine. Oxygen's farther along on this period than carbon, so oxygen's more electronegative, so you start with carbon. So let's go back. Start with carbon, right? Carbon, and arrange the oxygens around it. Link them with single bonds to start. We just use 1, 2, 3, 4 valence electrons. That leaves 12. So after you link everything with single bonds, you should satisfy the outside atoms first and leave the center atoms for last. So these oxygen need 6 more. 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. Perfect. Now all the oxygens are satisfied. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Each oxygen is satisfied according to the octet rule, and I've added 12 electrons, so minus 12 electrons leaves 0 left. Perfect, we're done. Or are we? We're not. Let's check. We forgot to check the carbon. How many electrons does it have? 1, 2, 3, 4. How many does it want? The octet rule says that carbon wants 8 electrons, but we don't have any more left to give it, so obviously we did something wrong. Now what else can we do besides place lone pairs? Obviously placing lone pairs on the oxygens didn't help, but they still have to be satisfied. So what we're going to do is we're going to try bonds, because that's something that both these can share since we ran out of electrons. So if we make 2 double bonds, that uses 1, 2, 3, 4 more electrons, leaving 8 left. So now, let's check the carbon. 1, 2, 3, 4, 5, 6, 7, 8. The carbon is satisfied. We can't add any lone pairs to it, no more bonds, that's it. So how many more do we have left? 8. How many more electrons do we need? Well, this oxygen needs 1, 2, 3, 4, 4 more. And this oxygen needs 1, 2, 3, 4, 4 more. What a coincidence. 8 divided by 2 is equal to 4. So let's just add those on as lone pairs because the carbon can't hold any more as bonds. And ta-da! Let's double check. We used 8. We have 0 electrons left. That's exactly what we want. We almost made that an 8. And now the oxygen, 1, 2, 3, 4, 5, 6, 7, 8 is good. This oxygen, 1, 2, 3, 4, 5, 6, 7, 8 is good. This carbon, 1, 2, 3, 4, 5, 6, 7, 8 is all good. We've used all the electrons and everything is satisfied. Here's our perfect Lewis dot diagram.